Alright, so in homework problem number 1, we got a 28.25 gram sample of water, and we're heating it from 22 degrees to 120 degrees C. And so what we got here is we've got a temperature change that goes from 22 degrees C to 120 degrees C, but we've got actually 3 different things going on here, because between 22 degrees and 100 degrees, we're heating up water. At 100 degrees, we're changing the phase, so we need a different equation there. And then after we change the phase, we're going from 100 degrees up to 120 degrees. So we really have 2 different changes of temperature here. Okay? And remember, temperature change is always temperature final minus temperature initial. Okay? And so temperature change number 1 is going to be 22 to 100, and that's 78 degrees. It's going up in temperature, so that's a positive change of 78.0 degrees C. Okay, do I need to show you the math? Everybody's good with that? Now, on a test or homework or something, whenever you're doing it, you need to show me your math. Okay, show me how you got it, because I want to know whether you got your sign right and what your endpoint was and that sort of thing. Did you know that the temperature for liquid water only goes up to 100 degrees. I need to see that, okay? If I don't see it, I don't know it. If I don't know it, I can't give you credit for it. So you need to show me that the first change in temperature is final temperature of 100 degrees minus 22 degrees, and that's where I get that first temperature change of 78.0 degrees C. And my second temperature change then is from that 100 degrees up to 120, so the final temperature is 120 minus 100 degrees C, and so I've got a temperature change here of positive 20.0 degrees C, okay? So I've got a 78.0 degrees C change for temperature, change of temperature 1, and change of temperature 2 is going to be 20.0 degrees C, okay? And then we've got to know the CP, or specific heat, for liquid water. And we need to know the CP for steam. And we also need to know the delta H for the phase transition. Okay? And the phase transition, this is between liquid water and steam. And so the specific heat for water, you have to memorize. You should know it's 4.18. Let's see, that's joules per gram degrees C. For steam, it's 2.02. Is that right? Okay, 2.02 joules per gram times degrees C. And the phase change energy, heat energy stored in the system, the change of that heat energy is what that delta means, was what, 2260? 2260 joules per gram. Okay, and we've got 3 different equations to work with here. The first equation, going from this 22 degrees up to 100 degrees, is Q equals mass times specific heat times the change in temperature. Okay, so we're going to calculate it that way. Q mass in this sample was 28.25 grams, 28.25 grams. The specific heat is 4.18 joules per gram per degree C, and the change in temperature for that first change, okay, this is our first Q, is 78 degrees. Put these 2 things over 1 to match the fact that we've got a fraction here, and we can see that we can cancel grams and degrees C. We're left with joules, and joules measures Q, and that's what we're trying to find, is what the measurement of the energy is. So 28.25 times 4.18 times 78.0, and I get 9,210.63 joules. We need to round it off to 3 digits because these 2 calculated numbers have only 3 digits. So we're going to underline from here over 1, 2, 3 digits. Those are going to be rounded off. We have to move our decimal place 1, 2, 3 places to put it between the first and second non-zero digit. So we can write our answer in scientific notation. And we're going to get 9.21 times 10 to the, since I moved it 3 places to the left, it's a positive exponent of 3. Okay? And so there's Q1, the first energy change. All right? Then Q2, for the phase change, Q2, is mass times the change in enthalpy. H stands for enthalpy. Used to be heat, that's why it has an H there. But it now is enthalpy for all forms of energy stored in the system. Okay? So you need to know what enthalpy is. And our mass doesn't change. It's the same sample of water, 28.25 grams of water. And the enthalpy change, when you change from liquid water to gaseous water, is 2260 joules per gram. Put this over 1, I can see clearly that I can cancel out grams. And let's see. Well, you guys done the math, right? Why don't you just tell me the answer? What's the unrounded answer? No, the unrounded answer. Oh, is that your unrounded answer in scientific notation? 63845? All right, let me do the math. 28.25 times 2260. Always do your math at least twice. 63845. 63845. Okay, and that's joules. And we need to round that off to 4 significant digits here. Really, this 0 is not, probably shouldn't be treated as significant, but it won't matter in the long run. Okay, so I'm going to treat it as if it's significant. If you treat it like 3 digits, that's fine. I'm going to let you do that, okay? Because this 0 should only be significant if there's a decimal place there. Okay? Remember, the 0's in the ones place. In the absence of a decimal place, that's a trailing 0. It's not significant. So really, should be rounding off to 3 digits. I will round it off to 4 today. Okay? So we're going to move our decimal place 1, 2, 3, 4 places to the left. And that comes down to 6.385 times 10 to the 4th. So your exponent should be the same, but you may not have this 5. You may have a 9 here. No, you'd have it yet 8 there because that 4 would only make that, wouldn't round that up. Okay. So either answer is correct. Okay, I'll accept that one, or I'll accept 6.38 times 10 to the 4th joules. Okay, we'll accept either answer today. All right, then Q3 is going to be where we're changing the temperature now from 100 degrees up to 120 degrees. So that goes back to that original equation where we had mass times specific heat times delta T. So we still have 28.25. We're still working with the same sample of water. But our specific heat number is going to be different. For steam, it's 2.02 joules per gram per degree C. And let's see, we got a change of temperature here of 20 degrees C. Our temperature change in temperature 2 is 20 degrees. Put these over 1 so that we can see to cancel out degrees C and grams. And rather than we have some debate over what the actual answer here is, I'll just do this one. And I got 1141.3. Got joules left. That's our unit of measurement. I need to round off to 3 digits. This calculated number and this calculated number have 3 digits. This measured number has 4. Those are the 3 numbers that matter when we're figuring out significant digits here. So we need our final answer to have the same number of digits as the one with the measured or calculated number with the least digits. Round off those. 1, 2, 3. Our decimal place is going to move 3 places to the left. So I got 1.14 times 10 to the 3rd joules. And then we have to add all 3 of these numbers together. You have to be careful about how you're rounding it off. So if we're using this version here, we'll only have 3 significant digits. If we're using this version, we'll have 4 significant digits in the answer. Okay? I'm going to give you both. I'll accept either answer. So let's see. 9.21 times 10 to the third plus 6.385 times 10 to the fourth plus 1.14 times 10 to the third. So when I add all those together, Q total, I get 74200, which we're going to round off to either 3 or 4 digits. So if you're rounding it off to 4 digits, your answer becomes 7.420 times 10 to the 1, 2, 3, 4, 10 to the 4th power of joules, or 3 digits is 7.42 times 10 to the 4th joules. So your second homework problem said, if 5 grams of iron at 65 degrees C is put in 100.0 grams of water at 20 degrees C, what's the equilibrium temperature? And it states that iron has a specific heat of 0.444 joules per degree C per gram. Okay? So let's see. We're going to have we've got 2 different things going on here. We have iron, which has an atomic symbol of Fe. And iron has a mass of 5.00 grams. It's starting at initial temperature of 65 degrees. So T sub I for initial temperature is 65.0 degrees C. And then we're going to put it in 100 grams of water. So we've also got water here. Okay, we could just symbolize that as W if you want to make it shorthand, or you could say H2O. Okay. And it has a mass of 100 grams, and we've got its initial temperature of 20.0 degrees C. We also know the specific heat of the iron. The specific heat of the iron is 0.444 joules per degree C per gram. We know the specific heat of liquid water, or you should now, 4.18 joules per degree C per gram. And so we have everything we need to solve this problem. We should know, you should know now, that Q for water will be, since water starting out as a lower temperature, it's going to be gaining energy, and it will equal the energy lost by the iron. So Q for water is going to equal the negative Q for the iron. And the equation here we're going to be using is mass for water times specific heat for water times the change in temperature for the water is going to equal the negative of the mass for iron times specific heat for iron times the change in temperature for the iron. But we aren't looking for change in temperature. We're actually looking for temperature final. And the temperature final for both is going to be exactly the same, because that's the equilibrium temperature. When the point where they have the same temperature is reached, they both are going to have the same temperature, so temperature final will be the same. Yes? Now, say what now? Will there ever be a time where like the negative goes with the water? Absolutely. If the iron was cooler than the water, yeah. All right, now, So really we need to plug in the fact that we need delta T is always temperature final minus temperature initial. Okay? And what we're trying to find is this term right here. And for both the water and for the iron, temperature final is what we're going to be looking for. All right? So we got mass for the water times specific heat for the water times, we're going to plug in that equation over here. Temperature final is the same for both of them, so I'm not going to identify that as either water or iron. But I do know that the initial temperature is for only the water here on this side. Close that parentheses. And that's going to equal the negative of mass for the iron times specific heat for the iron times temperature final again is the same on both sides, okay, because that's the equilibrium temperature. They're both going to reach the same temperature, minus temperature initial, and this is just for the iron. Okay? Now we start plugging everything in. So the mass of the water is 100 grams. The specific heat for the water is 4.18 joules per degree C per gram. The temperature final is what we don't know. Temperature initial for the water is 20 degrees. Okay? And so that's the equation, the initial equation for this side. And on this side, we're going to have the negative of the mass for the iron, which is 5 grams. The specific heat for the iron, which is 0.444 joules per degree C. I said it wrong, but there it is. Isn't that right? Okay, yeah, there it is. And then we've got this temperature final, which is going to end up being the same for both the water and the iron, so I don't have to put a different TF for the species. And then minus the initial temperature for the iron. The initial temperature for the iron is 65 degrees. Close that parentheses, close that bracket. Alrighty then, when I multiply this term times this term times this term, I get 418. So we're going to start out with grams times joules times T sub F over degrees C times grams. Okay? And we can see already we can cancel out grams. And so the second term we subtract here. We subtract here. So this term came from this times this times this. Okay? And then the next term is this times that. And we're subtracting because there's a subtraction sign here. And that comes out to be 8360 grams times joules times degree C over degree C times grams. And we can already cancel degree C and grams here. All right? Then, on the other side of the equation, we've got a negative sign here. And we take this term times this term times this term. And then we're going to subtract this term times this term times this term. So 5 times 0.444 comes out to be 2.22. And the units we have left are grams, joules, TF, over degree C, and grams. Grams times joules times T sub F over degree C times grams, and we can cancel out grams here. And we're subtracting this times this times this, and that comes out to be 144.3 grams times joules times degree C over degree C times grams. And we cancel out grams and degree C. Now I like to go ahead and distribute this negative, okay? So this is going to make 1 negative times this makes us a negative term, and a negative times a negative makes us a positive term. So this becomes negative 2.22 joules times T sub F over degree C times, grams are going away, okay? Cover that up, a little white out there. And then this negative times this negative gives me a positive 144.3, and all we have left are joules here. Okay, and over on this side, this doesn't change, except I'm going to go ahead and drop the canceled units. So 418 joules times T sub F over degree C times grams minus, what? Oh, I did cancel the grams, didn't I? Duh. Okay. I would have seen that in a minute, hopefully. Let's see then, and this term minus all that, we are taking out all that we've canceled already, 8360 joules. All right. What we want to try to do is to isolate the unknown here. To do that, we've got to collect terms. At least that's the term that I use for that. What I want to do is to add this number to both sides to get this over on this side. And then I want to add this term to both sides to get that over on this side. Okay? So here's what I'm going to do. I'm going to add 8360 joules to this side and to this side. What I do to one side, I must do to the other. Otherwise, it won't remain equal. And then I'm going to add to both sides this term, 2.22 joules times temperature final over degree C, and then plus 2.22 joules times temperature final over degree C. So a lot of you are not used to being careful and neat with your math. Okay? Trust me, I've been grading tests for you all semester. All right? It is really, really important that you're careful and neat with everything here. All right? Really important. All right. Then, when I take this negative number and this positive number that are the same, they pretty much go away on this side. Okay? And when I take this negative term here, it's the same as this term except that it's positive. This goes away on this side. And, Sure. Okay. And so when I add these two terms together, I get 420.22. I'm not rounding anything off yet. I'm going to round off at the very end. Joules times temperature final over degree C. When I add these two terms together, I get 8504.3 joules. Okay? All right, we're almost there because now we have it set up so we can isolate this term. Okay? We want to multiply the remainder over here, except for this, by the reciprocal. Okay? The reciprocal of these things right here. So times, and we got to do the same to both sides, okay? Degree C goes on top, 420.22 joules go on the bottom. And over on this side, we've got to do the same thing. We've got to take and multiply by this number on both sides in order to keep it equal. So degree C go on the top, 420.22 joules go on the bottom. Over here on this side, all of this cancels by that, and the degree C cancels there, so we've got T sub F by itself. Joules are canceling on this side. I've got degree C by itself, and we should know that degree C is a measurement of temperature, so we know we've got a really good chance we've set it up right. And we just have to do the math now. So T sub F is equal to 20.23773. You may not have as many digits as I do from my calculator. That's fine. And that's degree C. Got to round it off to, when you go back through the whole problem, and figure out the significant digits. So let's see. We started out with 4 digits and 3 and 3. When you figure it all out, add all the way through the problem, you end up with 3 digits at the end. So we're going to round that off then to 20.2 degrees C. Okay. Now let's ask ourselves, is this a reasonable answer? This is our reasonableness test, okay? We're going to look up here and see, okay, the answer has to be between 20 and 65 because it's going to equilibrate in between. Well, it is between 20 and 65 down here, okay? Should it be that close to water? Well, I can see that water's specific heat is nearly 10 times that of this, okay? So that's going to bring the temperature much closer to water than it would be to iron. And also, water has 20 times the mass that the iron does. So we should expect then the temperature to be much closer to the original temperature of water than to iron. Okay, it might be a little surprising it's that close, but that's the way it works.